to everyone. Today we are going to see about time response analysis problem. Let us see the problem. The open loop transfer function of a unity feedback system is given by g of s, which is equal to k divided by s into st plus 1, where k and t are positive constant. By what factor should be amplifier gain k be reduced so that the peak overshoot of unit step response of the system is reduced from 75% to 25%. Okay, here it is in 25%. We know that C of s divided by R of s is in transfer function, and also we know the formula G of s divided by 1 plus G of s into H of s. G of s is an open loop transfer function, H of s is a feedback of the system. Here they provide G of s value. You can substitute G of s value here, and also they said it is a unity feedback, so we can assign H of s value, which is equal to H of s equal to 1. We can cross multiply the s into st plus 1 with this one. We can get k divided by s square t plus s plus k. We taken out t is an outside, s square plus 1 by t into s plus k by t. We can move this t in the numerator. We can get k by t divided by s square plus 1 by t plus k divided by t. We can compare the second order derivative problem. What is in second order derivative? Omega n squared divided by s squared plus 2 epsilon omega n plus omega n squared. This is in second order derivative equation. By comparing the second order derivative equation, we can have a numerator part omega n squared, which is equal to k by t. From that we can find out omega n, which is equal to root of k by t, and we can compare the s coefficient to epsilon omega n, which is equal to 1 by t. From that we calculate epsilon, which is equal to, we can keep epsilon on the left side, we can move others 2 into omega n into the denominator part, and we have to get, you can substitute the k value, omega n, which is equal to root of k by t here, and we can cancel this t, and we have to get 1 by 2 into root of kt. Next we can calculate the reducing value of the gain. We can consider maximum peak overshoot is in 75%, so we can take maximum peak overshoot is in 0.75. At that time, let us consider the damping ratio is equal to 1, and the coefficient k value, constant value k equal to k1. Similarly, and one more peak overshoot they provide, it means a lower peak overshoot. It is in 25%, so we can represent it as in 0.25. At the time, let us consider epsilon, which is equal to epsilon 2. It means the damping ratio is in second damping ratio, and constant k is also, we can represent it as in k2. Next, we know the formula for an maximum peak overshoot, e power minus epsilon pi divided by root of 1 minus damping ratio the whole square. This is a formula for an maximum peak overshoot. We want to eliminate this exponential value, so we can take logarithmic on both sides. We can get ln mu p, which is equal to ln of maximum peak overshoot, which is equal to only this e power. It means that e, this should be cancelled, minus epsilon pi divided by root of 1 minus epsilon square. Squaring on both sides, we get we can eliminate this new denominator root value. We have to get epsilon squared pi squared divided by 1 minus epsilon squared. We can move to this 1 minus epsilon squared in the left hand side. It means that cross multiplication, it move to the left hand side. 1 minus epsilon squared ln of mu p the whole square, which is equal to epsilon squared into pi square. Next we can keep this ln value in left hand side. We can move to this part to the right hand side. We can get like this, and from that part we have to calculate epsilon squared epsilon squared, we have to get like this, ln of mu p the whole square divided by pi squared plus ln of mu p the whole square. We know that what is an lambda, it means that damping ratio epsilon 1 divided by root of kt, we found out in the previous slide, and epsilon squared, from that we have to squaring on both sides, epsilon squared we have to get 1 divided by 4 into kt. You can substitute this epsilon squared or replace epsilon squared with 1 by 4 into kt. Okay. From that we have to calculate what is in k value. This is an k value. We know that at peak overshoot 0.75, at the time k we can consider it is in k1. So we can represent k1 which is equal to 30.06 divided by capital T. Similarly, we have a maximum peak overshoot is 0.25. At the time k we can represent it as in k2. You can substitute the ln of 0.25 the whole square divided by 4 kt. We get t is in constant, you can keep as it is. We have to get 1.53 divided by t. What we have to find out, how many times it should be reduced, we have to calculate. So we can find out the ratio of k1 divided by k2. We have to get 19.6. It means that k1 should be 19.6 times as k2. 20 times it should be reduced. Like this we have to consider here. From 19.6 we can consider 1 by 20 we have to consider. From this final part, what we have to conclude here, the 20 times is reduced. Peak overshoot is 20 times is reduced. Then only the two constant values, maximum peak overshoot is the equal term. Thank you.